All right, so let me first try to finish the story that I started last time. So, so we had a construction of the link categories using ultrafilters. So this is going to be an ultrafilter on natural numbers, and we're always going to assume that it's non-trivial or non-principal. So this is just a collection of subsets of the set of natural numbers, which are almost everything. And so we have a notion of almost everywhere with respect to this ultrafilter. And then we took the category, let me call it C tilde, which is the ultra product with respect to this ultrafilter F of representation categories of GLN over C, or if you like, you can use Q bar. So if we take the product n greater or equal to 1 with respect to the ultrafilter of Q bar, or the product with respect n greater or equal to 1 over F C, this is still C, because it still is algebraically closed, has a cardinality continuum, and is characteristic 0. And so this category C tilde is huge, so it has objects of infinite length, so it's kind of a mess. But we have a nice object here, which is C squared, C cubed, so this sequence. And then we can take C is the subcategory generated by this V inside C tilde. So this means that we take arbitrary tensor products of V with its dual, and then direct sums of those, and take all summands inside that. And so this is a symmetric tensor category, and the theorem of Deligne is that then this C is equivalent to representations of GLT. And what is T? So T is 1, 2, and so 3, and so on. So this belongs to here. And this is any transcendental number. So how can it be any transcendental number? Well, I told you that this isomorphism isn't canonical, and there is actually no good choice of it. So every choice, and there is if you got one so this is going to give transcendental number under any such isomorphism, and if you change the isomorphism, you can obtain any other transcendental number. So that's the construction for transcendental T. But the question is, what should we do for algebraic T? And in particular for integer T. Because after all, for transcendental T, it's not very interesting, because we already have a much more explicit construction for transcendental T. So what we wanted to get is for integer T, we wanted to, this category was not abelian, and we wanted to obtain abelian envelope. So what should we do? Well, in this case, we should use the positive characteristic. So now I'm going to look at, instead of the set of all integers, I will look at the set of all primes. So I'm going to take the, so F is going to be an ultrafilter on the set of primes. Of course, it's the same, because you can just label the primes by integers. And so, so over the primes with respect to F of Fp bar. So this is, first let's look at our ground fields. So I claim that this is also C, because again, it is of characteristic 0, because we don't fix the prime. So the primes, we take all possible primes. And it is algebraically closed, because all of these fields are algebraically closed. And it is uncountable, and has cardinality continuum, because we just have sequences. So, so this is C. So that means that if I take the product, so now, but I want to obtain some algebraic number t. So let me take t, an algebraic number, and then it has a minimal polynomial q in z of x, minimal polynomial. And then there is a lemma in elementary number theory, which is nice, and which says that there exists an infinite set, let's say p sub q, of primes p such that q has an integer root n sub p modulo p. In other words, there are infinitely many primes for which q has a root in fp. So I will not prove this, but it is easy, although it is not easy to characterize such primes. So the example, basic example, of course, is that let's say t equals to I, then q of x is x squared plus 1. And it is known that the set PQ is just the set of primes. Well, it is the set of primes such that the equation x squared equal to minus 1 has a solution mod p. So by Gauss reciprocity, this is the set of all p such that p equals to 4k plus 1. And 2 also. Okay, but for higher degree equations, it's a very hard problem to classify, to describe these primes, but it is easy to show that they're infinitely many. And it's not going to matter for us what this set is. So also this number np, of course, it's an integer and it's defined mod p, so I can just fix some value of np. And then I'm going to take the product over all the primes p in this pq. With respect to some ultrafilter f. So the f is going to be on this set PQ now. The only thing we need about this set is that it's infinite. And I take representation categories of GL and P over FP bar. And this is going to be in Z plus, so that this makes sense. So this is some crazy category C tilde, but this has an object V, which is the sequence of standard representations. Vector representation for each of these groups. And then we define C to be the subcategory generated by this V. And this is going to be a symmetric tensor category over the product field, which is C, so over C. And so let us see what the dimension of V will be. So dimension of V is the sequence NP, where P is in this PQ. And so what is this sequence? Well, it's a certain complex number, but this number satisfies the equation Q of t equals 0, because NP satisfies this equation in the field FP bar for every P. And so, so this is some conjugate, some Galois, because it's a minimal polynomial, it's some Galois conjugate of, let me call it T tilde, or T hat. So this is not necessarily T, but this is some Galois conjugate of T. But again, this isomorphism is well defined only up to automorphisms of C. So we can always make identification. So that's exactly T. So can arrange that it is exactly T. And so if you do so, then there will be a theorem. And this theorem is due to my student, well, it was conjectured by no, it's due, actually this one is just due to my student Harman. Has graduated, Harman. And it says that the C is equivalent to rep. So it says what we need, that NP should go to plus infinity when P goes to infinity, so that these groups get larger. And in this case, this is equivalent to rep GLT when T does not belong to Z. And if it does belong to Z, we will obtain an abelian category, because all categories here are abelian, and abelian category is a first order logic property, so it goes along for the ride. So, and if T is in Z, then C is rep abelian GLT. So this is the envelope which I explained last time of Entova, Eisenbahn, Hinich, and Serganova. And as shown, I mean, they showed that their version of abelian envelope has a universal property, and using that you can show that all the other constructions give the same thing. And I should mention what these numbers NP are in this case. So if T equals Z, T is in Z, then can take NP, for example, just P plus T. This is the simplest thing. I mean, we could take, if T is positive, we could take just T, but that doesn't go to infinity. So the simplest choice that goes to infinity is P plus T. So this means essentially, so this ultra product is essentially a kind of limit. It's a model theoretic limit, as they say. And so essentially we say that rep GLT abelian, when T is in Z, is just the limit, and this is over C, the limit when P goes to infinity of representation theories of GL of n, well, of T plus P over FP bar. So the precise meaning of this is the above, but what it tells you essentially is that this category is responsible for the stabilization patterns in this representation theory when P goes to infinity and T is kept fixed. And by the way, I mentioned yesterday the connection of this category with supergroups. And what this implies is that there is some identities between characters of supergroups, GLMN, and characters of general linear groups and positive characteristic, which Harman derived from this business. And he also, one also has a parallel theory for symmetric groups and for orthogonal groups and for symplectic groups. So any questions up to this point? Okay, so then the next question is, what happens with rep GLT in characteristic P? So let's say K is an algebraically closed field of characteristic P. And we want to construct an analog of this category in characteristic P. So then we can try to run the same procedure. So we can define rep tilde of GLT. So T is going to be in K. And we can define rep tilde of GLT by diagrams, as I did yesterday. And then I can take rep GLT, its Karoubian closure. And then what we did, what we got in the case of complex numbers is for generic t, namely for t not an integer, the category rep GLT was semi-simple. And that was because the Wald-Brouwer algebra was semi-simple. But the problem here is going to be that the Wald-Brouwer algebra WRS of t aren't semi-simple, aren't all semi-simple for any value of t. So there is no value. Some of them are like the first W11, for example, it was a quotient. It was algebra with generator A, and A squared equals to TA. So T is a yeah, so what will happen is that they are not going to be for any choice of t, they aren't going to be semi-simple. That's what's going to happen. And it's understandably so, because if we take characteristic p, representations become reducible and things happen. So, so the question that arises is, can we embed? So things start to go wrong when we take when these numbers get close to p. Then things, because for small r and s, things are not going to be too bad. But when these things get close to p, then things will become bad. And the question is, can we embed this rep GLT into an Abelian tensor category, symmetric tensor category? So the same question, does there exist an Abelian envelope? And in this case, the answer actually in general is no. So what happens is the following. So this is because of the following lemma, which is very nice, and which says that suppose C is a symmetric tensor category over K of characteristic P, and X is an object of C, then the dimension of X, well, a priori it is some scalar in K. It must be in the prime field Fp inside K. So it can't actually be an arbitrary scalar if you have an abelian category. Of course, non-abelian, we have an example where it is an arbitrary number. But for abelian tensor category, it can't be. And this lecture is too short to give proofs, but the proof of this lemma is so short and so instructive that I will give it. So the proof is actually, it's short, but it's very instructive and in some sense rather deep. It says the following. So take P's tensor power of this object. And then we have a cyclic permutation. So it acts on this object. So in this case, sigma to the P's power equals to 1. And so that means that 1 minus sigma to the P's power equals to 0. So this means that 1 minus sigma is nilpotent. But in an abelian category, if you have a nilpotent endomorphism, then its trace will necessarily be 0. Because there is a filtration by kernels of powers of this element, and it's strictly upper triangular with respect to that filtration. That's where we use the fact that it's abelian. So since it's abelian, we can use kernels. This implies the trace of 1 minus sigma is 0. But what is trace of 1? Trace of 1 is just the dimension. So if d equals to the dimension of x, then this is equal to d to the p. And what is trace of sigma? Well, let us draw sigma as a diagram. So let's say p equals 3. So sigma looks like this. And then what does it mean, trace? This means that we have to close this up. And then we get a single circle, which means that this trace is just d. So this is d. And we get an equation d to the p minus d equals 0, which implies that d lies in the prime field fp. Any questions? OK, so what does it mean? Well, it means that we cannot have a lift when t is even in a quadratic extension of fp, in an fp square. But what if t is an fp? Does there exist a lift? Does there exist an abelian envelope? So if t does not belong to fp, no abelian envelope. Where by abelian envelope I mean envelope that preserves all the structures.
But not in FP.
Huh?
Not in FP.
Not in FP, yes. So what if t is an FP? And then the answer, so this is contained in the letter of Deligne to Ostrich. Letter Deligne to Ostrich, March 2015. So the answer is yes, but in many different ways. And so I will describe what are all the ways that this construction gives you. And for this purpose, so we can try to do it using ultrafilters. So let's take f, which is an ultrafilter on, again, the integers. And let's take the product over n greater or equal to 1 with respect to f of fp, for example. Well, this is a finite set, so this will be just fp. If we just take the same finite set everywhere, we will just get back that set, because what happens is there is p choices for elements, but the ultrafilter votes for one of them. So if you have a sequence, then one of the values, and exactly one, according to the axioms, is taken almost always. And so this is fp. Well, this is not algebraically closed. I could work with algebraically closed fields. Then if I put fp bar here, this will not be fp bar, but it will be some uncountable algebraically closed field of characteristic p. But that doesn't really matter. So let me work over this field, then I can tensor with the algebraic closure. So I can take the product over n greater or equal to 1, f of representations of general linear groups yeah, so we take these representations over fp, so this is going to be some kind of huge category, and so this is C tilde, and this contains V, which is the sequence of standard representations. And we can take the subcategory C, which is generated by this V. I can tensor this with over fp with fp bar, or I could just work with fp bar to start with, and then I would get some uncountable field, but it really doesn't matter. With k, if you like. So this is going to be a symmetric tensor category over k. And the question is, what is it? Well, let's see. So first of all, what is the dimension of V? So dimension of V, well, as usual, it is the sequence 1, 2, 3, and so on. But now it repeats. So this is elements modular P. So P minus 1, then 0, 1, 2, and so on. So periodic sequence like that. And so the limit is Fp. So this is some element T in Fp. So we see already something that we didn't really pay attention to before, that this answer depends on the choice of the ultrafilter. And this is kind of a bad news, because ultrafilters are quintessentially something that we cannot compute and cannot even define. And if our category ends up depending on this ultrafilter, then it is going to be a piece of junk, because we cannot really say anything about it. So better, maybe it can depend, but then it should depend on some parameters of the ultrafilter that we can compute. And well, it depends on this T, but this T is not so bad. This is something that we can compute. So suppose we fix that T, does it still depend on the ultrafilter when T is fixed? And the answer is yes. It actually depends on other things. For example, in characteristic P, in characteristic 0, if you take exterior power of object V, then the dimension of the ith exterior power of V is the binomial, is the T choose I. But in characteristic P, T choose I doesn't make sense. And therefore, in particular, wedge P of V, dimension of that is not determined by the dimension of V. It's a new parameter. So, and wedge P squared of V is a new thing that is not determined, its dimension is not determined by the previous ones, and so on. So actually, to understand what happens, let me say another thing about ultrafilters. So suppose that X is a compact metric space. And then everybody knows a theorem from basic analysis that every sequence in this metric space has a convergent subsequence. However, if you have the ultrafilter, ultrafilter on N, so this means that this sequence has has many subsequential limits in general, but what will happen is the ultrafilter is going to vote for one of them. And so lemma, if xi in X is a sequence, then it converges to some x in X with respect to f in the following sense. So we should just take the usual definition of limit, and the usual definition of limit says that there exists a point x such that for every epsilon greater than 0, almost all terms of the sequence are contained in the epsilon neighborhood of this point. So if we understand the words almost all in the sense of f, that would be the definition of the limit. So for any epsilon greater, and it's unique also to a unique. For any epsilon greater than 0, almost all members are in the ball around x of radius epsilon. Almost all with respect to the ultrafilter f. So that's a weaker condition than almost all in the usual sense, but that allows us to find a unique x. So how to prove this lemma? Well, it's very easy. So since it's a compact space, it can be covered by finitely many closed balls of radius 1. And one of those balls contains almost all terms of this sequence. Then inside that ball can be covered by finitely many balls of radius 1/2. And there is one of them that still contains infinitely many terms of this sequence. Then you do it for 1/3, 1/4, and so on. Then those balls are embedded, so they have an intersection point. And this point will have the property that for arbitrarily small neighborhood of this point contains infinitely almost all terms of the sequence. And it's also clear that this is unique because if you have 2 points, you can have 2 disjoint epsilon neighborhoods, and they can't both contain almost all terms of the sequence. And so now what we can do is the following. So let's take x to be the p-adic integers. This is a compact metric space with the usual p-adic norm. And then take the, so maybe notation is a limit when n goes to infinity with respect to f of xn equals x. So we take p-adic integers and then take limit n goes to infinity with respect to f of n. So n, an integer, is a point in ZP. In the usual sense, this sequence is dense. So every point is a subsequential limit. But the ultrafilter votes for one of them. And so this is going to be some t tilde in ZP. And clearly t tilde equals to t mod p. So it contains the information about t. And the theorem, which is conjectured by Deligne and proved by Harman, is that the category C depends only on t tilde. So the dependence on f is expressed through the dependence on t tilde. And the notation for this category, therefore, is rep GL of t tilde. So in other words, we see that Deligne category, Abelian Deligne categories in characteristic P do exist, but they are parameterized not by an element of the ground field, but rather by a p-adic integer. Now, how to compute this p-adic integer? Certainly, this definition with the limit is not very good because it requires the knowledge of the ultrafilter. But if we just have this category, how to compute this p-adic integer? Well, I told you that this has to do with dimensions of exterior powers. So here I want to bring up a theorem that we prove with Harman and Ostrich. That if C is any symmetric tensor category over K of characteristic P, then consider the series. There exists a D in ZP, unique, such that the sum from n equals 0 to infinity dimension of wedge n of x times z to the n equals to 1 plus z to the d. Now, what does it mean 1 plus z to the d? So I claim that if d is p-adic, 1 plus z to the d makes sense as a power series over fp. Well, that's simply if I write d equals to d0 plus p d1 plus p squared times d2 plus so on, where these are the digits, so I could write it like this way, d0, d1, d2, and so on. Then 1 plus z to the d is equal to 1 plus z to the d0. And then I have to do p d1s, but this is just 1 plus z to the p to the d1, 1 plus z to the p squared to the d2, and so on, where di are integers between 0 and p minus 1. So this makes perfect sense. So in other words, this means I could write this 1 plus z to the d as the summation of d choose I, z to the I. And so this means that d choose I makes sense for d in ZP. So if we have d in the field of characteristic P, then d choose I is not going to make sense when I is bigger or equal to P. But if we have a lift of this number in Fp, if our element of K is in Fp, and we moreover fix a lift of that to ZP, then all these binomial coefficients start to make sense. But they do depend on all the digits of D. So what we see is that these abelian envelopes of this category depend on lifts of this number T to the Padics. So the first digit is T, but all the other digits are to be chosen. And so the digits dj are simply the dimension of wedge p to the j of x. So in other words, the things that you need to prescribe are dimensions of wedge p to the j of x for all j, and then the dimensions of all the other exterior powers are determined by that. Any questions about this?
So this is still connected to this down here somehow, yes?
Connected to what?
The last thing on the previous board.
Right, yes. So this is how you calculate this p-adic number. Its digits are given by this formula. Yeah, so this D is really T tilde, yeah. Okay. So that's basically the story. And I should mention that all these, so this gives you some abelian categories, and they are all non-semi-simple. So actually, we don't know, they have non-moderate growth. Of course, they are similar to rep GLT in characteristic 0. But they're all non-semi-simple, and there is an open question whether there exists a semi-simple symmetric tensor category of non-moderate growth in positive characteristic. This I don't know, and actually I'm leaning towards a negative answer. But I can't be sure.
Just say that again. Just say it again.
So open question. Does there exist a symmetric tensor category over K with characteristic P of non-moderate growth which is semi-simple? Okay, so now I want to go back to the topic of my third lecture, which is categories of moderate growth.
You said your money is on no?
I expect no, but I'm not too convinced. Because actually we didn't know, before Delin explained to us this construction, we didn't really know, didn't know what to believe, even for non-semi-simple ones. So categories of moderate growth. So we discussed that in characteristic 0, categories of moderate growth are all that we know very well, representations of supergroups. But in characteristic P, there are some counterexamples. So the question is, what do all the categories look like in that case? So let me remind what we did. So first of all, we defined, so if C is a symmetric tensor category over any field K of any characteristic, then we defined a notion of negligible morphism, f from x to y, negligible if for any g from y to x, trace of fg equals 0. And they form a tensor ideal. N. And then we can define C bar, which is C mod n, with the same object, but morphisms quotiented by n. And this is called the semi-simplification of C. And the reason for that is that it's a semi-simple, tensor category, symmetric, and its simple objects of C tilde, C bar, are the same as indecomposable objects of C of dimension not equal to 0.
C bar is the
Right, C bar is a semi-simple category, yes. So, and so this shows that the category in some sense becomes simpler because it becomes semi-simple, but on the other hand, it becomes more complicated because usually classifying indecomposable objects is a very hard problem and the classification is wild. For example, if you take even something as simple as the group Z mod 3 cross Z mod 3, it is known that classifying indecomposable representations in characteristic 3 of this group is a wild problem, and there is a huge number of them of all dimensions, and so all of them will become simple objects of our category. So really, these categories are crazy, but even though they have finite length, everything is okay. They just have a lot of objects. So what we should study is not those categories themselves, but we should study subcategories generated by some objects, still similarly to what we had here. Not because of infinite length, but because of just a huge uncontrollable collection of simple objects. And then you might ask me, it's on the same board, this question. There is an obvious idea trying to address this problem. Take these categories of the line, which have non-moderate growth, and take semi-simplification of them. Or maybe semi-simplification of some subcategory. Or maybe semi-simplification of them and then subcategory generated by some object. The answer is, so won't it give a positive example for this thing? Well, the answer is, in most cases, I don't know how to compute this. But in those cases when we did compute it, it turned out that when you take semi-simplification, it kind of shrinks so much that it loses this property and starts to have moderate growth. And so, so it doesn't. Possibly that would be, if I were to try to find an example, that would be the thing I would do. But I don't know how to compute the semi-simplification, and so this remains an open question. And then we considered an example when we had the group Z mod P. That's an example that is tame, that we can actually handle. There are finitely many indecomposables. So there are indecomposables J1 up to JP. And in the semi-simplification, so we always have the semi-simplification functor from C to C bar. But it's a monoidal functor, but not a tensor functor in our sense, because it is not exact on the left or on the right. That's what's required for a tensor functor. And so C bar is a category with objects L1 through LP minus 1. So this gets killed because it has dimension P. And this is the unit. And then we had this multiplication law, Lm cross Ln, equals to the sum over I, greater from 1 to a minimum of m n p minus m p minus n of L m minus n plus 2I minus 1. And this is a truncated Clebsch-Gordon rule, which in mathematical physics is known as Verlinde rule. Because this is the fusion rule that occurs in the Wess-Mina-Witten model of two-dimensional conformal field theory, which is just the fusion rule for representations of affinely algebra SL2 hat at level k, which is equal to p minus 2. Or you can take a quantum group at q equals to e to the, let's say, 2 pi I over p. Sometimes people take pi I over p. There is some subtle difference, but it is not relevant to what I'm talking about. And so this is why this category, we call it Verlinde. This category was introduced by Kazhdan and Sergei Gelfand, and also by Georgiev, Mathieu in the 90s. And it is, but I'm going to denote it Ver-P because it categorifies the Verlinde rule. That's how Ostrich denotes this category. And so that's a semi-simple category, and it does not have a functor to vector spaces other than for P equal 2, and to supervector spaces other than P equal 2 and 3. So Verlinde 2 is vec, so that's very simple. Verlinde 3 is actually supervec. But if you start with 5, Verlinde P, it has a tensor product decomposition. Verlinde P plus tensored with supervec. And this is just generated by L1 and LP minus 1. And this is generated by Li with I odd. So the even spin representations, if you like, because I is the dimension of the representation of SL2. And incidentally, so maybe I don't have much time, but let me make a remark. That the fact that it contains supervector spaces is quite nice. So you take this P minus 1 times P minus 1 Jordan block, and it plays the role of the odd line in this theory. So this in particular means the following thing, that if we take a Lie algebra, let's say, suppose G is a Lie algebra with action of the group Z mod P. For example, you have an element of order P in the corresponding algebraic group. Then we can view it as an element of rep, as a Lie algebra in the category of rep Z mod P over K. And then we can attach to it through this functor, semi-simplification functor, G bar, which is going to be a Lie algebra in Ver P. And in particular, well, we have Gi, which is home from Li to G bar, or G bar I, if you like. And so then we can have G bar 1 and G bar. This is going to be an ordinary Lie algebra. And if you add G bar P minus 1, this is a Lie superalgebra. So from ordinary Lie algebra with actions of Z mod P, even starting with P equals 3, we can obtain Lie superalgebra in characteristic P. And this is very useful because it's actually, people have worked on classifying simple Lie superalgebras in characteristic P. And for small p, this is a very hard problem because even to construct these Lie superalgebras is very difficult. So there are some papers by El Duc, by Leites, by others, which try to construct. So it turns out in characteristic 3 and 5, there are many exceptional Lie superalgebras that are not related to characteristic 0 or to higher characteristics. And they take pages and pages to construct. But what you can do is you take, for example, exceptional Lie algebra such as E8, and take, say, P equals 5, and take some element of order 5, and do this construction, and it immediately spits out those examples, many of them. But this is just a nice remark to make on the way, but it's outside of the main line of narrative. So this is an application of this theory which has nothing to do with tensor categories. So now, so the question is that one might ask is, well, so this starting from P equals 5, this is a counterexample to Deligne's theorem. So you can ask, maybe it's the only counterexample in some sense. So maybe you just need to replace supervector spaces with this category because this turns out to be incompressible. It doesn't map into smaller categories. So the goal is to map our category by a tensor functor to a symmetric tensor functor to as small category as you can, as simple as you can. Then your category will be realized as representations of some group scheme in that smaller category. And if that smaller category is simple enough, then maybe you can classify group schemes, at least, let's say, simple, semi-simple ones, and understand what all possible categories can look like. So does any symmetric tensor category in characteristic P map to ver P by a symmetric tensor functor? And the answer is, well, surprisingly, in some cases, yes. So there is a theorem of Ostrich. Yes, if C is fusion, which means semi-simple with finally many simple objects. So this is a remarkable theorem. It's really amazing that one can prove this. So it kind of tells you what the fusion categories, symmetric fusion categories in characteristic P look like. And the conjecture of Ostrich, this also holds for infinitely many objects. So still semi-simple. And I don't know how close we are to prove this, but this is not out of, this is not impossible that we will know this in a couple of years. Now, why is this useful? So see, for example, this means that for semi-simple categories, at least definitely for fusion ones, the usual Deligne theorem holds in characteristics 2 and 3. Because in that case, the category is nothing new. So Deligne theorem holds, at least for fusion, in characteristic 2 and 3. So why? How could this be applied? So I said mentioned modular representation theory, which is a very classical subject. It's representations of finite groups and positive characteristics. So what does it have to do with that?
What does it mean here when you say Deligne holds?
Deligne theorem. So the theorem that in characteristic 0 that any category of moderate growth. So we are considering right now only categories of moderate growth, and any category of moderate growth maps to supervector spaces. And so the same holds in characteristics 2 and 3, at least for fusion, and for general semi-simple ones if we believe this conjecture. For non-semi-simple ones, it's false, and I'm going to say about that in a few minutes. But so how do we apply this to modular representation theory? So what do we want to do in modular representation theory? So for example, suppose G is a finite 2 group. And suppose X and Y are odd-dimensional indecomposables. Let's give an example. Z2 cross Z2 cross Z2. This is already impossibly difficult group. Z2 cross Z2 is still tame, so you can describe everything. But already for this one, there is no classification of these indecomposables. Representation over K, where characteristic of K equals 2, and algebraically closed. And let's take their tensor product. Well, it's odd dimensional, so at least one summoned will be odd dimensional. And so Benson's conjecture. Dave Benson conjectured and checked in many, many examples that X tensor Y has a unique indecomposable summand of odd dimension. Now, what does this conjecture, how is it related to what I was talking about? Well, when you take odd dimensional, so representations, it's exactly the simple objects in the semi-simplification of the representation categories of this group. So X and Y is in rep G bar. So this conjecture is, Benson conjecture is equivalent to the statement that all simple objects in rep G bar are invertible. In other words, that this is what is called a pointed category. So pointed category. Because if we take X and X dual, for example, then we know what that odd dimensional summand should be. It should be the unit representation, the trivial representation. So that would mean that in the semi-simplification, X tensor X dual equals to 1. And so it's invertible. But what does Ostrich conjecture tell us? So Ostrich conjecture tells us, well, that there is a functor from this semi-simplification to vector spaces. So this means that this semi-simplification is the representation category of some G tilde, where this is a linearly reductive affine group scheme. Linearly reductive is stronger than reductive. It means that representations are semi-simple in characteristic P. That doesn't hold for reductive groups in the usual sense. And linearly reductive schemes were classified by Nagata many years ago, and they're very easy to describe. So Nagata's theorem so this is, I think, 1960s, says that G tilde has the following structure. So we have a torus. Then we have dual scheme to finite abelian 2 group. And then on this thing, there can be an action of an odd order finite group. So that's what such schemes look like. And so Benson's conjecture is equivalent, therefore, to Ostrich's, follows from Ostrich conjecture plus the statement that gamma equals to 1. So this is actually not necessary, but in all examples, this gamma equals to 1. So, well, it's kind of believable that odd order groups won't appear all of a sudden out of 2 groups, and that's what happens in examples. And so this is how it's related. So we envision some applications to modular representation theory. And maybe I should just, can I have 5 minutes? Yeah, so I will maybe say what happens in non-semi-simple case, because it's just kind of interesting. So for the non-semi-simple case, actually it's pretty easy to find a counterexample. So non-semi-simple. So in this case, this Ostrich's conjecture doesn't hold, fails. And there is a very simple example in characteristic 2. So we just take Hopf algebra D, which is k of D over D squared. So D is just a primitive element. So this is really the simplest infinitesimal group scheme that you can imagine in characteristic 2. And of course, representation category of D is perfectly nicely maps to vector spaces by forgetful functor. So it's not a counterexample, but we can change the commutativity map. So we put an R matrix, which is 1 tensor 1 plus D tensor D. So this means that the braiding is going to look like this. So C of X tensor Y will be Y tensor X plus dy tensored with dx on a module. So a module, so an object of this category is a vector space with a differential D whose square is 0, and its commutativity map look like this. And so this is this category rep dr does not have a map to vec. So we were wondering, in fact, you can obtain this category. We always say that there is no superspaces in characteristic 2 because there is no signs. But actually, it's not quite so. If you take super vector spaces over two adix, or rather over the ramified extension of the two adix where you adjoin square root of 2, then this has an order over the integers in that field such that its reduction modulo square root of 2 will be this category. So it is a kind of version of superspaces. And since Verlinde category has a component superspaces for every p greater than 2, we were hoping that this is just what you have to do. In characteristic 2, you have to replace. But it turned out to be false. So the question is, does everything map to this D, representations of D? And the answer is again no. So Ostrich found a counterexample. So you can adjoin to this category. You can adjoin an object X such that X tensor X is equal to D, the regular representation of this D. And then the combinatorial dimension from Frobenius-Perron dimension of this X will be square root of 2. So this is just if you take what is Frobenius dimension. It's you take your object and you multiply by simple objects, and this gives you a matrix. And this is the largest positive eigenvalue of this matrix. So this has dimension 2. So this must have dimension square root of 2. So this can't map to vector spaces because of the irrational dimension. And it can't map even to this category because here the dimensions are all integers. And this category is a reduction mod 2 of the Ising model tensor category, which is Virasoro representation at central charge 1/2. So then we, of course, with less hope, we're hoping maybe this is the ultimate one where everything maps. But no. So in fact, we found with Benson so we have a whole sequence of categories. C0, and this is just vec in characteristic 2, is contained in C1, and this is just this rep D, R. And this is contained in C2, and this is this rep D, R, to which we adjoin this X, in C3, and so on. So there is an infinite sequence of categories which are symmetric tensor categories in characteristic 2 and which are incompressible, which means that they don't map to smaller categories. Any symmetric tensor functor out of this Ci is just the inclusion of that Ci to a bigger category. It can't really shrink. And these things have, like I said that this category Verlinde P, for example, of K, is it's a reduction from characteristic 0 of Verlinde P over C, which is just category which arises in mathematical physics, affine Lie algebra at level P minus 2. Or rather, you need to work over QP bar, which is isomorphic to C for the reason that I explained before. And the similar thing holds here. So this is so Verlinde 2 of C is just vector spaces, and it reduces to this. And this is Verlinde 4 at root of unity of order 4. And C4 is a Verlinde 8, and so on. So it's powers of 2. And these categories are just Ver plus, which is the even spin ones. So this is not completely proved, but this is partly conjectural. But the main conjecture is that a similar picture should exist in characteristic P greater than 2. that in fact there exist reductions mod p of prime power Verlinde categories in characteristic 0, which come from affine Lie algebras at level k equals to p to the n minus 2. And those will be non-semi-simple if n is greater than 1. And we expected the ultimate category to which everything maps is just the union of all of them. So we constructed these categories in characteristic 2 and studied them in great detail. They're very, very interesting. And many open questions about them. We also studied the putative categories in characteristic p greater than 2. And we know many of their properties, but we still haven't proved their existence yet. Because for that, you need to establish some kind of order in these characteristic 0 categories so that you have good reduction mod p over a local ring, like ZP of ramified extension of ZP. OK, I think probably it's a good time to stop. So thank you very much.